Uh, Thank you all for a thank you for this nice introduction and good afternoon all. Today I am going to talk about optimization of lithium plating mechanism for nonlinear cycle life degradation in LFP cell. Actually, thanks to some of the people present here, they have already spoke a lot about degradation today. So I'll skip some of the initial slides where we speak about the lithium ion, its basic chemistry, and what causes the aging and degradation. So even before starting that, I would like to say that I have come from Mahindra Last Mile Mobility. We are working in Bangalore, and our unit basically looks after the small commercial vehicles, and we have we have our office in 3 locations in Bangalore. One is the corporate office, and the other 2 being the plant and the innovation center. So with this, and we have our products already running in the market for last few years, and they are also the EV based products, I mean, and they are performing well, and there is a good customers appreciation from them. So anyway, today I will be concentrating my talk mostly in the cell level study that we do from our team, and trying to understand what is going on during aging. So as this lithium ion movement goes on within the transfer moves, lithium ion movement goes on from cathode to anode and anode to cathode in charge discharge. So there is the process of aging that happens, and that is already been talked of. Now this in this aging process, in one stage is reached where there is a very fast degradation that sets in. So our objective is always to delay this fast aging process, or that is the catastrophic degradation process. So through this modeling approach, we are trying to understand what is the process going on inside and how to slow or rather to delay it. So whenever we look into the aging mechanism, there are a lot of details that comes up, and if we have to understand it, mainly externally we don't see all these phases being happening, but what we see that there is the aging varies with the number of cycles or the ambient conditions and C rate in which it operates. But even then we are not able to understand that what is the process that is actually causing this degradation to go on. But the one of the thing that right now we have learned for sure is the ACI formation. So what happens is that in the anode side there is always this solid electrolyte interface formation that takes place. That is obviously a very important part for the performance of the cell, but also this has this takes part in bringing about the degradation over as the cell runs for several cycles, or even if the cell is not utilized for a long time. But along with that, we have many other degradation process like structural disorientation, passive layer formation, lithium plating, etc., which we are not able to understand that at which stage this processes sets in, or how each of the process starts working within the cell. If we have to understand it through some testing and diagnosis, it is a humongous activity, and it is impossible to pin it down. So only simulation is the best approach to understand it. So in this electrochemical simulation that we have done with GT Auto Lion, we have converted this process into a series of equations, that is the electrochemical equations which take care of all the processes that is working within the cell. So this comprises of the charge conservation, the diffusion, solid diffusion, ion diffusion within the electrolyte, and then the diffusion across the solid liquid interface. So this is the main part, that is the diffusion across of the lithium ion across the solid liquid interface, which drives this process of degradation, and all this process that goes on, that is actually linked by an Arrhenius kind of equation to take care of the temperature constraints that is actually playing that actually happens, or that is actually a practical scenario. So in this software, before we even go into the degradation aging, first we have to make the basic model of the cell. So for this we have in the software only, we have used this to first give the basic inputs like the material of the battery, the cell components, and the different geometrical parameters related to the cell, and some thermal features and interfacial definitions like the diffusion constants and all, to generate a basic model. And in the these are put into the simulation software to generate a basic discharge and thermal profile. But and these profiles we try to match with our test data, which we obtain in our cell testing. If it is matching, it's well and fine, but if it is not matching, then it has to be optimized, and this optimization of initial parameter goes on with in some loops until we are able to get a set of parameters with the capacity close to the capacity of our cell, some reasonable porosities, and also through this through this exercise we are able to come across to some of the parameters which we cannot get from the supplier. Actually, this full exercise of electrochemical simulation requires lot of inputs from the suppliers, and often we struggle to get those informations out of the suppliers. So through this optimization process, we actually get a ballpark value of this parameters like mass loading, the electrode thickness, NP ratio, etc., which are very important parameters, and this ultimately helps us to develop the basic cell model. So this model finalization we did. After that we did some validation, and there we could validate our test results for 25 and 45 degree with very high accuracy, relatively high accuracy, and we could even model the temperatures also. We could match them, even the chargings also we could match, and in charging usually comprises of a CC and CV phase. In the CV phase, which is a kind of a relaxation phase, and with autolion we had some initial glitch to model the relaxation part, so we could max at the max, we could still go close with the CV phase. So all these things when we validated, then we got significant confidence with our model, and we took it forward for our aging analysis and aging modeling. So here again, we from this finalized model, we started with the calendar aging and the cyclic aging. We had the data for this, and we use some of the aging parameters like aging mechanism. We activated some of the aging mechanism in the software to first see how close we are with our test result. And so again this went on in some loops through some optimization protocol until we came up with some ballpark value. Now so this is the first thing we did, that is the calendar aging modeling. So the calendar aging is so in this particular phase of the cell. So when the cell, this happens when the cell is not running, it is in the idle stage, and here what happens is that the main degradation that drives this kind of degradation is the ACI formation. So we activated the ACI formation mechanism to optimize or to model this calendar aging. From there we could pin down the process parameters, and which were with a confidence that it was having a good fit with the test results in our calendar aging test result. When the same parameters were used for predicting the cycle life in 25 and 45 degree, here also we could predict it with good accuracy, but only towards the initial part in case of the 25 degree. But in 45 degree test data, we could see it went into a full proper match. Now the next part came that why this catastrophic degradation is coming up then. That means apart from ACI, there is some other degradation phenomenon which has started to play its role, or it has onsetted, which is causing the fast-paced degradation. So after several literature survey, we understood that this could be one of the reason could be the lithium plating, and then we activated the lithium plating in the model. But the interesting part is this, that the lithium plating is a mechanism which won't start in the beginning of the degradation mechanism. So here actually what happens is that this will happen only under certain conditions. Like it will only happen when the metallic lithium starts depositing. It separates out of the electrolyte and it starts depositing on the anode over the ACI as metallic lithium. And when this kind of process starts, this actually catalyzes the process, and it forms into dendrite, and this can puncture the separator, reach the cathode, and it can cause short circuit. So this is a very critical part of the cell, and once this kind of mechanism sets in, it is an indication that the cell is going to die very soon. So we have to understand that from the external trend of the degradation, that when to stop, or whether the cell has reached to that point where it should be stopped, or which then it will not be able to perform any further. So we, after activating this lithium plating, we could see that it went into a good match with the test result, and till like 80% SOH, and so this was observed in the 25 degree case. In the 45 degree case, where we have tested till 80% SOH, there we have seen a continuous monotonous linear degradation all along, and this particular phase never came up. Okay, or rather when we tried to generate the plot through model, then we saw that this phase is coming up, but it is coming at a much later part of SOH, that is when it goes beyond 75%. So we tried to understand that what is it that is actually, or how this process is actually been taking place in the model. So we looked into other aspects such as the lithium loss. What is the kind of lithium loss that is happening? So here we see that when there is only the ACI degradation, I mean in this case both the ACI and the lithium plating degradation mode is active, but in the initial phase only the ACI formation is playing its role till 1200 cycle, around 1200-1300 cycle, and after that the lithium plating loss is setting in, and then the loss of lithium is going very fast, and that is adding to the faster loss of the capacity. Whereas in the case of the 45 degree case, there where we have tested till 600 cycles, we couldn't see that the lithium plating phenomenon to start at that point of time, but it is starting much beyond that process, which we could not test because of some other issues. Okay, so now this process that plating has set in, it will happen if the anode potential goes below zero. So we, from this model, we tried to see that if that is the thing that is really happening or not. So this is what actually happens within a cell. When we cycle a full cell, we are able to see the voltage plot that is given in black. But in the half cell reaction, it goes, the cathode side voltage grows as shown in red, and the anode side voltage change as shown in blue. So over the cycle, as the the internal resistance goes up, the blue voltage plateau that you can see, or the voltage curve you see, it keeps on dipping, and time comes when it goes below zero. The axis is given on the right side for the blue. So it goes below zero, and this is the detrimental part, and this causes the lithium plating to occur. And we tried to monitor this anode potential in our cycle life simulation also, and we actually observed that this is starting in 700 cycle in case of the 45-degree case, and 1200 cycle in case of 25-degree case. And so the model also took care of the beauty of the modeling of this modeling approach was that even we activated both the mechanism in the beginning, the plating was not working in the beginning, and it waited till the anode voltage reached to 0 volt, and at that point it started its action. So with this we tried some once we got the confidence with the model, we tried to simulate some cases to understand that how to delay this lithium plating behavior. And we saw that if we decrease the this discharge C rate, then it can be delayed as shown here, and in case we reduce the C rate, the charge C rate, then it can be eliminated, or almost eliminated, as it is going a full linear kind of it was showing full linear degradation at least till 2000 cycle. We didn't do the simulation any further. Even then this model could be used to even capture the effect of DOD or capture the effect of smart charge, which are still like our ongoing projects. So even we tried to do the same, use the model for simulating our MIDC discharge profile, and there also we could see a good match. So this with all this, we can say that this developed electrochemical model is based on mostly on the ACI formation, and later part it is the lithium plating that is playing its major role. And this lithium plating was this nonlinear degradation of the cycle life happened. It showed up in 25-degree case, which was caused due to the lithium plating, and this lithium plating leads to faster, is going to faster, like it is exhibited with faster loss of lithium, fast-paced loss of lithium as the potential goes below 0 volt. And finally, this model could be used to strategize different solution of charging techniques, and also to strategize like some condition specific C rates for our discharge as well. So thank you. So I thank GT Autolion and their team for the support, for developing the understanding and helping us out from our team to generate this model and to bring it to this stage. And now I'm open for some questions.